So my talk is on the potential pitfalls and the successes of computational design, and I'll describe what I think computational design is in a second. What I'll talk about is I'll briefly talk about what we are, format. We're relatively new. I'll talk about very, very briefly research. Being quite vain, I'll talk about me, I'll talk about some of our recent work, all this very briefly, but then I'll talk what is computational design. So I'll give one explanation, then I'll talk about the good, then I'll talk about the less good. I don't want to depress you, but I think we'll leave with the less good. So format, as Ashley mentioned, my background is I was Director of Ramboll. First Whitbybird, then Ramboll. I formed the computational design team in Ramboll. Myself and a few others left to create format. We're a small consultancy based in Bath, actually, but we're working on projects across the world and some extremely complicated ones. And format itself is made up of me with my background, a bit of ex-Bureau Happold, a bit of McNeil, the people who publish Rhino. We also have a chap who's a mathematician and an architect. So it's quite a diverse mixture. I mentioned research. And one of the things we set out to do is to really try to push. We firmly believe that structural engineers have got more to offer than just structural engineering. We want to get pure research. We want to use our skills in geometry, design in its broadest context. So we are really trying to push that if we can. And about me, that's me, obviously. I talked about myself, so we don't really need to talk about this much longer. But before I start recent work, it did strike me that I cut across one of my, I suppose, cardinal sins in the sense of, we're quite passionate about computational design and the tools and the opportunities, etc. But there's a tendency to actually focus on the funky projects and the flashy projects and all the whacked out Zaha type stuff. But the reality is, this work is, I think, equally applicable to the 95% of very, very necessary work that we do. So apologies in advance, I forgot my golden rule and pulled together a presentation full of all the whacked out, mad stuff. So I think we need to bear that in mind because, as I said, these are tremendously valuable tools, and I'll emphasize tools again later. So just to sort of set the scene, some of our recent projects include this timber spiral reciprocal structure that we did for Burning Man in 2016. It's 8 meters tall. It's made from very, very standard pieces of timber, and part of the fun was to make all the standard pieces of timber fit together. All, again, modeled in some of the software I'm going to describe, all modeled in a very collaborative environment with the architect. We ended up having, I think, 5, 6, 7 people standing on top. It was designed for 100 miles an hour wind, which every structure at Burning Man has to be, and unfortunately it was burnt at the end. So no record remains of the structure. So that's one. I'll talk about this a bit more later. This is the pod. It's a small transportable listening recording pod for the BBC with Fathom Architects. Aperion Flow, a cardboard structure with an architect called Adam Holloway from the University of Westminster and Oxford Brookes University. This was the whole city of culture. It's quite interesting making a structure of this form and this material. How do you deal with that? Again, I'll talk about this later. An oldie for us, this was a bending active timber grid shell with the University of West of England. Again, I'll talk about this later, but there are some very interesting conclusions as regards computational design embodied in that project. And some of the stuff we're working on at the moment, there's an 18-metre tall work of art somewhere in London, all from stainless steel, coming to a street, probably not near you, because it's in inner London and very expensive, soon, as well as increasingly larger scale projects, such as this competition for a laboratory building in Berlin. We're also working on a 200-metre long timber power station. So there's a whole broad range of stuff. So what is computational design? Now, I think my interpretation is a very personal interpretation. Is it design with computers? Well, yeah, it is. Is it BIM? Well, no, I personally don't think, and I won't be talking about BIM as part of this presentation. For me, and I'll touch on this later, computational design is design. It's a tool set. It's a tool set in the same way a pencil is a tool, or a calculator, or a scale rule, or your own imagination. All we're doing, we think, is creating a richer tool set. It's not a religion, it's not a new form of architecture, it's a tool set. As I said, we don't think it's BIM, or at least I don't think it's BIM. BIM is great, but I'm not going to talk about BIM. So what I will do is to show you as an example one specific project which maybe weaves together lots of the aspects of computational design. This is one of 2 timber cabins we're designing just north of the Arctic Circle in Norway. And it really is perched on, well, one of them at least, it really is perched on a cliff like that. So it's a very challenging environment. There are a few structures knocking around at the moment where the double curved surface has been broken down into flat panels. We think in our Ramboll days we were the first people to do that, so we have no shame in doing similar. So taking that project as an example of some of the techniques we think may embody computational design, this, and I'm sure many of you know what this is, but this is a computer program called Grasshopper. It's actually an add-on for the 3D modeling package Rhino. And it's not all about Grasshopper. Again, there are many other software packages which embody or contribute to computational design, but it's a good example. And here, our modeling process has literally been encoded as a series of steps. Each of these components manipulates, in this case, I think, a series of curves which define the overall structure. We can add parameters such as the size, width, height, blah, 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 but we could also encode other things as well. So think of it as a linear scripting or mathematical process which leads to an outcome. So everything I show you in here is going to be modeled within that environment. So we're able to manipulate the overall form by changing some global parameters, but manipulate the overall form with structural feedback. So we can have take a sensible view of, is flatter, better, wider, taller, whatever. So we can embody some global modeling. We can embody, again, within the same file, literally, we can embody how we can break down this surface into smaller, manageable patterns. In this case, how the panels, the cross-laminated timber panels, are broken down to flat, 6-sided elements that are easy to fabricate on a simple fabrication machine. We can embody how the connections work, so we can detail the connections. We can put the connections in areas of lower stress, for example. We can model the wind loads as a reaction to the shape. So they're very tuned to the shape of the structure, the form of the structure. I think with an accuracy which wasn't possible before. It's subjective as how accurate this is, Bromout's wind loads, but I think it's at least heading in the direction of more quantifiable design. We can look at the areas of stress, we can zoom into those. Again, all of which exist within this framework or this process, the computational design process. But as I mentioned before, it's a tool. We don't think of this as a religion. Some of my employees do, it must be said. Which I'll talk about that later. So it's like a pencil. It's like, sketching. This is super old school. This is tracing paper and ink pen. So think of it in the same vein. It can be part of the creative process. It can be part of the delivery process. It can be all those things together. But it is just a tool set for us as engineers to exploit. So, having described who we are and trying to get a sense of what computational design is, I'm going to talk about what I perceive as the good, and what I perceive as the bad aspects. I think briefly to summarize, what I think is good is I think it enables us to transcend structural engineering in some ways. We can encode inferences from other fields of science or engineering. We can get back to the raw physics of engineering as well. We can see how that works within our structures. It gives us the ability to deal with complex forms. And I started by saying I didn't want this to be about complex, mad projects, and then went to town including complex and mad projects. But I think what it enables us to do is, as I said, to really refine, gives a lean design, which is equally as applicable to the 95% of the projects we do. It gives us a chance to design for simplicity in production as well. So we can model with one eye on how it's going to be built. And I'll explain that more in a bit. And it can make us more productive as well. I think in the wrong hands, it can make us less productive. But again, I'll touch on that later. So when I say go beyond structural engineering, I think one of the things I'm passionate about is us as structural engineers having this fantastic technical-based education. We are creative thinkers. And I think there's an opportunity there for us to go beyond structural engineering and look at pure research, look at industrial design, look at geometry, etc. And I think we are the people who can own that in the design process, or at least take a really active role in the design process. And that's something else which kind of bugs me. And I teach architecture school quite a lot. And I'm slightly fed up with the phraseology. Right, it's now time. We finished your design lecture. It's now time for your technical lecture. And I'm brought on. For me, it's, we are designers as well. So I think part of this is going beyond structural engineering. And as an example, I mentioned this before. This is the pod. So it's a mobile listing pavilion for the BBC. It was designed by Fathom Architects. We didn't do the structural engineering. As far as I'm aware, there wasn't actually a structural engineer on this. It's all made by the stage company. But what the architect wanted to do was to encode the first words ever used, I think, in it's either a radio broadcast or a recording of the radio broadcast, which was something like, "Is it snowing where you are, Mr. Robinson?" So there's a set there. To record that history, they wanted to actually represent the sound wave of those words as part of the facade of the structure. So we were engaged to model that and to model ways in which those sound waves could be represented as pixels as part of the facade, but also how those sound waves would not interact with each other in such a way that it would look ugly and messy. So we encoded all sorts of dampening routines and such like that. So we were able to pass on our script. And as I said, we were engaged as purely a sort of geometry scripting only consultancy to the architect. They finished the facade. Oh, we're getting mad, look. Sorry. So we trained them in the use of the script as well, so they're able to make their own changes if they wanted to. So I think that's a good example of us as structural engineers offering more than the norm. A couple more examples. This is a work of art that we're doing, which is actually pretty confidential. It's a massive, massive thing. It's all made from solid tubes. We are doing the structural engineering, and we've looked at this in terms of how we optimize the structure using clever evolutionary solvers and things like that. But the really interesting thing is we're also engaged to take the underlying geometry and to rationalize the underlying geometry into something which can be built and is affordable. So in this case, the architect's original scheme was for these members here, which are extremely big, actually, in real life, as a series of double curved splines. So the curvature was varying along its length. It would have been a nightmare to fabricate and would have cost many, many millions. So we undertook to break down the double curved splines into a series of single radius arcs in such a way that they all fit together at a common tangent. So you have a much simpler version of that. So there's a computational design process which fits as best as possible single curvature arcs to double curved line. So by doing this, we're able to shed a load of money, bring it in budget, and it becomes a viable project. So and the reality is we do this in association with all the optimization, the structural modeling, etc. And a whole ton of hand sketching and everything. So again, that's beyond structural engineering. Ashley and I were talking about this earlier. This is a cast bronze screen outside the Wellesley Hotel. Again, we are not the structural engineers. We've been engaged through the geometry modeling with the artist. Each of these bronze buds is set out on an underlying cast bronze screen, which is an open mesh screen, which looks a bit like, which is that. So the artist spent, I think, weeks actually chopping up and modeling the screen by hand. So we wrote a bunch of scripts and plugins for the artist so he could do all that Boolean cutting and all that slicing himself. Again, it saved a lot of time in the workflow. An oldie but a goodie from my ex-Ramboll days, Milan Expo 2015. Daniel Libeskind was the architect. We were presented with a pattern of tiling, ceramic tiling, where every single tile was a different size and shape. And again, it would have just killed the budget. So we devised, again, a series of routines to break down the surface, or break down the tiling pattern rather, so there were as many tiles of the same shape and size as possible. And I forget the actual number, but I think the number went down from 12,000 different tiles to 12. So again, it was a huge saving. We did all the structural engineering as well, but again, this is all structural engineers going above and beyond. There's just the tiling pattern. So yeah, I firmly believe these tools give us the chance to go further than every day. And as I said, I keep saying, I think these tools give us a chance to tackle the 95% of projects we do, to make them more lean and more efficient. But I also think they enable us to encode more influences from outside in our design process, in even our early design process. And this, for example, is a canopy project that we're working on. It's missing a lot of the structure. It's just got the top half. And these are all this is a CFD, Computational Fluid Dynamics add-on for Grasshopper that enables us to change the size, inclination, shape of this, as well as all the tension in the fabric here, all that sort of, and to see its influence upon the wind load. Because in this particular case, the wind load was probably the single biggest driver on design. So we're able to encode that as part of our design process. And I think an earlier and slightly fuzzy example, again from the old Ramboll days, was a similar project we did for Oxford Brookes School of Architecture, where they commissioned a series of super tall steel trees. I think the biggest one actually was circa 7 meters tall. And Ramboll at the time, I still do, have a room full of supercomputers which could give you the CFD modeling in quite a fine detail. but we're able to take their raw results and import those into our grasshopper model, which was our analysis model, to get a really good sense of how the wind pressures varied over the structure. So again, we're able to tune the design. So again, this was something we're able to really encode or squash into our design process. Look like that. In the end, still there as far as I'm aware. Whoops, sorry, back. This really probably should have gone in the engineers going beyond section, but also I think this does work as a very good example of encoding different influences. Again, from our old Ramboll days, and it's still research that we're doing now, so it's looking at automatic generating of master planning. Well, it doesn't have to be master planning, it's just forms and shapes that are determined by lots of different criteria at the same time. So here was a case of working with a London-based architect and developer, looking at ways you could automatically optimize tower forms in relation to solar shading, shadow casting, neighborhoods with existing buildings, etc. So I think, again, it's a tremendously interesting thing for a structural engineer to get involved with, but it also shows how much, again, you can include within this basic design process. So again, I think that these are two decent examples of the advantages of computational design. A few more physics-based solvers, and this is something we're quite keen on. It's getting back to the raw physics. We've been heavily involved with writing a plugin for Grasshopper, actually, based on a physics solver in Grasshopper. And we have a series of components that do structural analysis using that plugin. It's called K2 engineeirng, if you if you want to download it. And essentially, it enables us to bend and deform structures and then see in real time how the bending moment changes, but also the form it takes if you apply a force. So it's particularly helpful for bending active structures. It's extremely useful in looking at buckling, so we can see how members buckle and really map their behavior over time. We've used this in a few projects. This was a project that was a research project that was done as part of the Smart Geometry Conference. So I'll gloss over that. But a lot of our work was, or rather the first time that we really used this was for the UE Pavilion in University of West of England. So these are a series of bending active thin timber laths. So if you bend a very thin piece of timber, what form does it take? Literally, what shape does it take? So putting aside the essential material uncertainties of plywood, we are able to predict what form something bent will take, as well as all the bending pre-stress that's in it. This is the world's most dull video, which shows it happening. We can look to see where it's buckling in real time. I don't know why it is so slow. So for us, it's a tremendously useful tool, getting down to the raw physics. We can look at the traditional structural engineering output and the displacements and bending stresses and all that sort of thing. So but essentially, this works within our computational design process. So again, it's another tool that's embedded within the way we work. And I think one more example of physics-based solvers. This is actually for, bizarrely, a bridge, but not an actual functioning bridge. It was a sculptural representation of a bridge in Cincinnati, where the artist we were working with had the commission to build something across the historic street in Cincinnati, which was representative of the city. So he chose one of the 7 bridges across the Ohio River, which goes between Cincinnati and the next city, which I have to look that up. So essentially, it's a series of carbon fiber rods which are bent and then there's a cable representation of the bridge in the middle. So you bend the carbon fibre rods, and they're able to map what shape the cable takes inside this series of carbon fibre rods. So it was the cables that was the bridge, and the carbon fibre rods were the bending active way of forming the shape. So that is hopefully still ongoing as a project. Again, I think what's good about computational design, it gives us the ability, I think, to deal with complex forms. And I mean, banging on about the fact it's not all about complex forms. Well, it isn't, but it does. Does give us that inherent advantage. I mentioned this project before, which is the Amperian for Whole City of Culture. It was a card structure, an extremely large card structure, actually. I think this is something like 8 meters long, 4 meters tall, working in conjunction or collaboration with an architect called Adam Holloway, who did lots of the modelling himself of the connections and the shape. And he was able to give us that grasp of a model. We could run with that, and we can do some more structural analysis and some more tweaking of the form. Such as, for example, we were able to say, well, look, we can do a basic structural analysis of the original shape. But what we can also do is to automatically modify the underlying shape such that you can tweak the form within set parameters. You can't go mad. You can say, change the form within 100 mil in this direction, 100 mil in that direction. And then we were able to refine the deflection from 190 mil down to 104 mil with just very simple automatic manipulation of the global form. It's a moot point where 100 mil is actually acceptable. But in the case of I think a card structure, it's fine. And in reality, it was built and performed beautifully. This one I mentioned before, Burning Man, 2016, a highly complex reciprocal spiral. Again, the fun was to try to make this out of simple, repeatable elements. We did another Burning Man structure with the same team the year before, and the year before that, actually. But the one the year before was an extremely complicated, digitally fabricated timber structure, which they couldn't finish. They started building it, they just ran out of time. And the lesson learned was it was just too complicated for its own good. So I think for future Burning Man projects, there's now that knowledge that we can row back slightly and use simpler techniques to build things. So, but this was a highly complex geometrical form that used a sine curve as an underlying guide. Again, we're able to use the same file with the architect. We can collaborate on quite a deep level. We can encode the structural engineering into all this. So it's again, it's a very interesting tool, a very useful tool when you're dealing with forms and shapes that are inherently very complicated. Another advantage, I promise there aren't many more advantages left, but another advantage is we think this gives us the opportunity to design for simple fabrication. Part of being able to do simple fabrication is experience. Part of it's also a challenge as well. We quite like the challenge of designing some of these pavilion structures, knowing we do not have an unlimited budget. We do not have a robot cutting machine. So we've only got a 3-axis cutter, or we only have simple materials to play with. A lot of our work has been done on that basis. So we're able to encode routines and techniques which automatically sort a structure out to give us simple joints, to give us simple 6-sided members so they all converge at a point where there are only three nodes coming together, so it's a super simple connection. That sort of thing. And in this case, again, this was the UE pavilion, we were able to fit lines of structure over what's called lines of geodesic over this double curve form, such that when you actually lay each of these flat, they're completely straight. So all you're doing is you're making this complex, curved, three-dimensional form with completely straight members. And it's obviously very cheap to do, it's very quick to construct. It didn't take long to build at all, it just used student labour. I think the total budget was something like £6,000 to build the whole thing. Pretty strong. It was only supposed to be there for 2 weeks, and it lasted a year and a half. And it's only now starting to get a bit saggy, and I think they've taken it down. So, it's a good example of building with, sort of designing with pre-constraints in mind. A similar project, going back to our Ramboll days, which is the on-greening pavilion. Again, used pretty similar techniques of splitting down a double curved surface into simple, flat, straight elements. So you can interrogate this surface and fit what is simple stuff to it. So I think we like the challenge of designing with the simple rather than designing with a massive budget. A few more examples. This was the Milan Expo pavilion I alluded to before, where we were able to just do simple slices through the model and fit what looks to be quite complicated curved steel structure, but actually it's turned out to be a relatively simple thing to fabricate. It looked like that. Looks mad, but actually it was on time, on budget, and the first thing to be built on site. So it was, again, a relatively simple process. We were able to break down the rain screen panels of that structure into very simple elements of, it wasn't plywood, I think it was some sort of particle board in the end. But how do you break this down into super simple elements that someone on site can cut up with a saw if they have to? So again, there's some great computational tools which help that. Racing around slightly, I think another advantage of computational design is, I keep saying it widens our tool set. Not only can we encode physics and CFD, etc., we can go really beyond that. So here we're taking a laser cloud survey and using that to inform our hut structure above the Arctic Circle. But one really interesting example is another sculpture that we're working on. Again, this is sort of off the press stuff. There's a series of very shaped elements connected together to form a 3D space frame. But what we've been able to do, and what we've been able to do in conjunction with a good friend of ours from the University of West of England, is to create a tool set for Grasshopper called Biomorpher. And what Biomorpher is a evolutionary solver, so it uses the law of genetics to actually literally search for a problem space to find the most efficient solution. But in this case, there's a quick video. It gives you an amount of control, because these things exist in other forms. There are other plugins which do this, but essentially it's a black box. What you'll say is, I want the answer to be like this. Give me the form which matches that answer. What Biomorpher does, it gives you the opportunity to say, right, okay, stop. Now, let's look at the different variations you've come up with. And I can pick ones I like. You'll see this in a second. So it's actually saying, look, here's the design history. So it cycled through these designs, and it thinks these designs are the ones which best meet the criteria. And well, okay, I quite like these ones. So you can select a more refined tool set and then go. So it's essentially dipping into the design process. We can introduce coding, raw coding. In this case, this was the same tree structure I mentioned before for Oxford Brookes. But at a very early stage, we're able to code the pattern of perforations in the stem and the leaves of this structure so that they weren't bumping into each other, and they reflected whatever stress was in the structure. And we're able to show different variations to the architects to give them a sense of how it would behave. So, the introduction of coding into the design process. Bit like that. Further. success of computational design, at least for us, I think a real success in-house as a small practice with very few people, but doing some quite large projects, is there are some nice tools which really work from a productivity perspective. So we were able to take what is our 200-meter long timber structure that we're working on, automatically analyze it within this computational design toolset, do the structure analysis, but also spit out, so there's a render of it, but also spit out the BIM model as well. So in this case, we can change the angle of the frame, we can change the depth of the members, etc. We can really tune the structure and then spit out the BIM model at the end. And we do this quite a lot at the moment with our projects. And again, we think this is quite a nice example of the 95% of rectilinear projects rather than the whacked out crazy ones. Some more views. The BIM model, pretty straightforward stuff. And on the same project, we were able to, at the outset, before we even had this timber structure, to really rapidly look at different options for how you'd span that big space. So we looked at 2D trusses, we looked at 3D trusses, we looked at catenary structures, we looked at diagrids, automatically varying diagrids. So you're able to actually produce these conceptual designs very, very quickly. And I think these were started 2 days before we were due to present, and we're able to give different tonnages and sizes during the first presentation. So again, some huge advantages if you can harness the software. And I think the last success, lean design. Again, we have the power of the computer harnessed to what is our, hopefully our innate creative design mindset. This was a very small piece of structure. We do sort of product design as well. In this case, it was a base plate for a canopy that was probably only about this size, but it has to get anchored down. It has to be small enough to be transportable and light enough to go in a standard FedEx package. So we looked at it being a single aluminium sheet, automatically cutting away material where it wasn't needed to reduce weight. This is otherwise known as topology optimization, but again, it's another example of a successful application of computational design. And pretty much the first project we ever did as format was bizarrely an art gallery outside Barcelona, where you can see the arrangement of all the rooms, where there's actually some pretty large spans. So here's a reinforced concrete structure. Because of the large spans and their proportions, and I think the architect's real interest in the 1970s, skip to that, he was very interested in the waffle slab, so sort of thing that's gone out of fashion, but really wanted to sort of push that back. There are good reasons for doing this in the gallery, actually, in terms of acoustics and reducing weight. But essentially, we were able to analyze the entire structure as a single plate, and then to specify a reinforced concrete waffle slab that had varying depths depending on how hard it was working. And actually, that's reasonably hard to construct. And there are other options where you vary the pitch. So you say, there's a 600 by 600 module, there's a 900 by 900 module, there's a 1200 by 1200 module. What's the best fit for those modules for the underlying stress of the structure? So that's it. I think, I think some of these are hugely successful techniques, but there are some less good, I think, the less good criteria that we should be aware of, which includes what we think is an unhealthy early constraint on the design process, communication breakdown, inherent pre-constraints, different from unhealthy early constraint, but inherent pre-constraints in the design process, recycling of design, which propagation of errors, over-reliance on technology, And in fact, this is a black box. You know, I've been talking about genetic algorithms and funky shape-shifting things, but this is very much, crap goes in, but crap can come out. And you can't see the intermediate stages. So this can be a black box. In terms of unhealthy early constraint, there have been some interesting studies on this, where when you look at the amount of design freedom you have, so this is the life of a project. So at the very early stages in conceptual design, you have the most freedom. You have the most freedom to do something, scrap it, start again. You do all sorts of ideas. So inherently, this is the most fuzzy, loose part of the project, in a healthy way. We can, all sorts of ideas are fluid and are in motion, and we should encourage that. Also, a project is what's called a wicked problem, where it's difficult to know what are the main criteria that actually lead to the success of a project. So, for example, if you look at a tower project, the amount of criteria that you need to try and kludge into your design is tremendous, and it's difficult to actually isolate what is the single most effective criteria. So I think one of our contentions is, if you start doing this sort of thing at a very early stage, you lock down the 3D modeling, you do a nice script, you do some coding, etc. You've got it to a stage where you think this is pretty cool, this works. Actually, you're cutting across the healthy fuzziness of the beginning stages of a project. And I promise not to be rude about BIM, but I think one of the issues of BIM that we found, because we know Scandinavian architects pretty well, and often in Scandinavia you're required to do a BIM model right at the competition stage. And the problem is that once you do that, once you lock down the symbolic relationship between different parts of the building, or you define it symbolically into slab, beam, column, etc., it's very hard to get away from that. It's it's difficult to do this. Let's scrap it and let's start again. Let's throw it up. And often, projects I've been involved with, some of the best designs we've had probably only originated at stage D onwards. So you'd probably lose the opportunity to go back and pursue those designs if you're symbolically locked into a representation of the structure. I'd also say that mentally it's quite difficult, because I think one of the criticisms I have of, let's say, our staff, being honest, is that the script becomes the challenge, in the sense of, I've developed this fantastic script which deals with the problem. It's beautiful, the logic is fantastic, it's very neat, yet the engineering of the output is actually secondary to the script. So one of the things I have to keep pushing people is, it's not all about the script, it's about the output. So again, they've invested a huge amount of emotional time and effort into producing something pretty cool. And what I was also talking to Ashley before about, actually, is you invest time optimizing. You use these really interesting, fantastic techniques to optimize a structure, make it super lean. One of the projects we're working on, it's the one with all the long stems. At the end of our design process, we ended up with a structure that was beautifully refined along its length. Each of the diameters was exactly spot on, etc. But it's actually pretty impractical to build and to fabricate. And the simple solution would have been to say, well, let's make this a 219 diameter tube here, let's make these straight links, etc. But again, we've invested a huge amount of time and effort into making it spot on, ignoring or forgetting about the practicalities. So we think the digital design process can lead you astray if you're not careful. It can also lead to communication breakdown. This is literal spaghetti. Now, I keep banging on about how these tools and techniques are great for collaboration. We can swap a file between ourselves and the architect. But there are occasions where I pick up something that I did myself a month ago, and I can't work out what I did. So it's very hard in terms of communication to pass this stuff around. It can be extremely confusing. And people have different ways of doing the same script. There's so many different ways of doing it. So communication breakdown is a real concern. And I cast around the digital design panel for some more examples. And Paul Jeffries, ex of Arup, now of Ramboll, gave me this example. Well, this is the national, I think it's the National Tennis Stadium in Qatar. And his comment was, he set up this digital model that was super refined. It enabled you to analyze the structure, spat out pretty much the fabrication drawings. It did everything. But the problem is, he was the only person who could actually use it. No one else in the design team had the same level of skill that he had. So if he was hit by the number 74 bus, the project would have been in real problems, but it also meant that he had to do everything himself, pretty much. At least that's what he says. But I'm sure, I think we've experienced the same thing. Where again, we've invested lots of time and effort into some of the particularly skilled members of our staff coding something from first principles, and you think, well, what happens if they literally get hit by the number 74 bus? So communication is a worry. Philosophically, also inherent pre-constraints. Now, again, one of the beauties of this process is we can encode parameters in a script that we can change, and the form will automatically change, regenerate, etc. But who's to say those parameters are the right parameters? Who's to say? You're applying a pre-constraint on the design process by doing that. And things like biomorpher and evolutionary solvers are a way of trying to break out of that pre-constraint. But they themselves also start with opening parameters. So I think there's a critical appraisal of what we're actually putting in as our starting conditions in some of these models. There's an issue, I think, in recycling design. And again, we're very guilty of this. You spend ages building up a script which does something, and you can either cluster this together into a small script, and then you say in the next project, well, that worked really well. I'll just nick this bit, and I'll reapply that to the project. Not knowing, of course, there could be all sorts of inherent errors in that script, and who knows if it's appropriate in the first place. So this is a common theme with apparently real software design about recycling design of recycling code is very much frowned upon. There's an over-reliance on technology. Cut straight to this example. This was a timber grid shell, sorry, a bit fuzzy, timber grid shell that we did where all the members were digitally fabricated, all cutting patterns produced from the model, blah, blah, blah. Very accurate. Sorry. We had what we thought was a super machine to do it. We trusted the super machine. Unfortunately, all the holes are in the wrong place. So all the pieces arrived on site with all the holes in the wrong place. So luckily, the architect who was literally building this himself, actually, got on the phone to the fabricator and managed to persuade the fabricator it was his fault. Brilliant. And he made them all three. So it was, we got over it at the end, but don't trust the technology, essentially. Double check. This particular grid shell was outside the Millennium Dome. I'd forgotten to include a picture, but I think it's still there. That's the one. Yeah. A few more. I mentioned black box. No idea what's going on some of this software because sometimes you're dealing with highly complex forms. This is something we are in the midst of designing. Again, it's confidential, but it's on a ski slope in a German-speaking country in Europe. It's a timber structure. It's actually a lot more complicated than it looks here. And it's all on it's part of a research project as well. It's part funded by the local university, and the idea is you build, again, very thin elements. Or what happens if we tension those elements? We create a bent active form, and we can use our K2E software to look to see what bent active form it takes, which is brilliant. But go back to that. Each of these will actually be a bent active truss, and this will be a bent active truss, and these will all be bent active trusses. And there are supports, there's wind load, and there's all sorts of things going on. So, trusting the answers. If you can get an answer, can you trust the answer? Well, we think the only way is just to break it down to very small, simple elements. So, I think one of the things to take away from this lecture is that, firstly, not trusting the computer is fine, but it's about validation, and it's about checking, and it's about breaking it down into small, manageable components, which you think, pretty well represent what's happening in the complex form. But always have that in mind. So we broke this down to simple panels, simple elements, looked at the stress in simple elements and how they're all working together, etc., blah, blah, blah. So extremely important that we do that. And the last slide from me, again, courtesy of one of my colleagues on the digital design panel. This is a report on a reinforced concrete structure where literally some of the columns were missing, and the contractor built it. And whoever it was who did it blamed the BIM model for missing the columns. But essentially, it's not the fault of the computer, it's the fault of the person checking it. Or the lack of checking. And at risk of leaving on a slightly sort of negative note, I think whatever you do in terms of manipulation and using these fantastic tools, what you've got to do is check it. Check what comes out. So that's it from me.